Hi, we're Team 15. My name's Anand. I'm working with Rex, Jamila, Noel, and Clay, and we're working on the MDmouse, which is a computer mouse that has integrated blood pressure in it. Some background on hypertension or high blood pressure. It infects about 1 in 7 people worldwide, so it's very common. On top of that, this can lead to cardiac disease, stroke, and heart attack. And along with that, there's also comorbidities such as with COVID-19. The largest problem is that measuring in a clinical setting, while accurate, comes with caveats such as not being able to do it often enough, daily blood pressure fluctuations, and white coat hypertension, which just means nervousness within a clinical setting. On top of that, self-monitoring devices are largely inaccurate. This is due to motion drift, which just means the movement of your arm or finger within inside the device, and then a lack of calibration on these devices. So there's a clear need for a more accurate personal device.
So as Anand just mentioned, existing blood pressure categorization techniques fall short largely in terms of frequency of measurements with the doctor's visits. You can't go to the doctor's office every day, obviously, and the accuracy and usability in terms of the various at-home blood pressure monitors. Additionally, the gold standard, the mercury sphygmomanometer, as I can personally attest, is physically cumbersome to use and painful to use repeatedly. So again, there needs to be a new option. So to basically describe the need a little bit more, we need a device that's accurate, easy to use, comfortable so we can use it regularly, say at home or in the workplace, and it needs to be efficient so it doesn't interrupt workflow or general lifestyle characteristics. That's the main need.
So we talk about why we need a personal blood pressure monitoring device, but why should it be a computer mouse? One of the main goals of the device is for it to be convenient and easy to use. A computer mouse is something that most of the working class uses for a large part of their day. Someone would not have to go out of their way at all to take a blood pressure measurement with their computer mouse. Additionally, since the mouse connects to the computer via USB, there is a built-in power source for the mouse as well as a built-in display to show the results. As it is already a fully manufactured device, we want to clarify what our role in the MDmouse is. As is, the mouse is not very accurate or precise. It gives a wide array of measurements and is often inaccurate. For example, the measurement seen here is measurement taken by the device and is quite low and not accurate for this user. Thus, our goal is to make mechanical modifications to the device to try and improve the accuracy of the device.
So working off of the basic user needs, again, we need accurate measurements. We need to include all necessary information relating to blood pressure, and we need to make sure that the device can hold the adult index fingers dimensions and generally should be efficient. So in terms of those specifications, we decided that they need to be within 5 millimeters of mercury. It must display all the necessary measurements, and again, full adult human index finger circumference.
With all of those considerations, the direction that we took for one of our designs includes consideration of the fact that the material that the tubing was made of was so flexible that it was actually increasing the signal attenuation. And so that's something that we worked to limit by changing the tubing to clear rigid tubing. And additionally, the configuration of the tubing involves many bends, many 90-degree bends, which you can see in the figure all the way to the right in light blue. So most of it is horizontal, but then there are 90-degree offshoots. We realized that we could decrease the number of these offshoots by changing the configuration of the housing that connects to the dark blue pump. And we would still be able to maintain, with the new casing structure, we could still maintain the stability of all the components. We could reduce the number of 90-degree bends, which would reduce the pressure loss and further attenuation. And we were able to accomplish all of this by 3D modeling and printing in ThinkBox. Additionally, I'd like to show you the drawing of the cross-section of the tubing that was maintained from the original design, which is to the left, and a more up-close image of the newly designed casing to the right, which now has U openings that are more horizontal, that allow the tubing to include fewer 90-degree bends and decrease attenuation.
So while working on the device, our group gained access to a mercury sphygmomanometer, which is considered the gold standard of blood pressure measurement. And so this is what we use to both characterize the need, the level of improvement that our device needed, and is what we will use to test how much of an improvement our modifications have made. So in order to do that, we have already compared the unmodified device to the mercury sphygmomanometer using a student's T2 test for accuracy, as well as a variance measure for the precision of both devices. And once we make our modifications, we then plan to see if the accuracy and also the precision of measurement have improved afterwards. Preliminarily, so with our initial testing, we were able to confirm the need for the device. Systolic and diastolic measurements are less accurate at higher blood pressures with a correlation value of 0.97 and 0.78 respectively, showing a strong correlation. And the mouse variance is significantly greater than the sphygmomanometer, which shows that the mouse is not nearly as precise. So where do we go from here? Well, our next steps are we plan to fully construct our prototype. We have finally received the materials in order to do so, as well as we plan to test our finished prototype in the same way as our preliminary results in order to see if there has been a significant improvement. These are our references. I'd like to quickly thank Terry Malloy, Dr. Colin Drummond, Dr. Matthew Williams, Aidan Friedrich, Pratyush Chera, and the National Institute of Biomedical Imaging and Bioengineering of the National Institutes of Health for their help in supporting this project. Thank you all very much.